Start? All right, good afternoon, ladies and gentlemen. Thank you for being here today. Today we'll be presenting to you our senior design, as everybody else, which is a biodiesel pretreatment system. Our team is made up of Harrison Mejia, Fabian Torres, and myself, Renier Rodriguez, and our advisor is Dr. Andres Treman. This shows you a quick overview of some of the main topics we're going to be covering today. Some of the more important ones include our objective, our actual final design, our testing, our results, as well as the global components. So what exactly is biodiesel? Biodiesel is a renewable, clean burning alternative to traditional diesel. It can be used within any diesel engine without having to necessarily make any modifications to the engine whatsoever. It is mostly produced from recycled vegetable oils and animal fats. They actually go through a chemical reaction known as transesterification, which is when glycerin is removed from either the vegetable or the animal fat, and what's left behind is the biodiesel. The figure here shows you the production of biodiesel in the U.S. for the past decade. As it can be seen in the early 2000s, the production of biodiesel in the U.S. was in the low millions in terms of how many gallons were being produced yearly. However, in 2011 and 2012, this number skyrocketed up to 1.1 billion gallons each year individually. And then only in last year, in 2013, it went up again to 1.8 billion gallons. We can expect these to actually continue to grow as the consumption and the demand for biodiesel continue to increase. Right now in the U.S., we have around 200 biodiesel producing plants, which are capable of producing around 3 billion gallons of biodiesel a year. So as mentioned earlier, biodiesel is mostly produced from recycled vegetable oil. This is better known as waste vegetable oil, or WVO. Waste vegetable oil contains all of the important properties required to produce the biodiesel. However, it also contains debris and water. It can be classified into two main categories. We have yellow grease, which is simply vegetable oil that's been used to cook, and it now contains small amounts of water as well as debris from the food that was cooked in it. And the other one is brown grease. Brown grease is typically much more contaminated in terms of how much water and debris it has. This is due to the fact that brown grease is actually caught within the sewer system by grease traps, which explains why it has so much more water as well as debris. Some of the main advantages to using waste vegetable oil to produce the biodiesel rather than going out and purchasing clean oil are that number one, obviously it's a lot more cost efficient to purchase the dirty oil, purified, and then use it to produce the biodiesel. And number two, since we're dealing with a recyclable product, we're moving towards a greener future. So with that being said, the objective for this senior design is to create a system which will purify the waste vegetable oil into a final product that is suitable in order to produce biodiesel from it. We wanted to make sure that we had an adjustable system. What this means is that depending on whether we have yellow grease, brown grease, or anything in between in terms of how contaminated the oil is, we can actually adapt the system in order for the oil to take different paths throughout the different filters that we have. So our design goals are to, number one, we want to obtain a final product that is at least 99% pure oil. So what this means is that once it goes through the system, the debris as well as the water content within that oil is less than 1%. And our motivation is to, number one, we want to become more independent in terms of producing our own fuel rather than having to go overseas to purchase it. We want to invest time as well as gain knowledge in alternative fuel solutions, since we all know fossil fuels are eventually going to run out. So it's good to start investing time now. And finally, as mentioned earlier, we are moving towards a greener, more alternative, more environmentally friendly future. So as far as our design alternatives, most of our research went into finding different ways that oil is clean right now, what different filters are using. Some of these include filtration by magnets, chemical filtration, filtration by means of gravity, and this one behind me is a centrifuge, which is actually one of the components that we ended up implementing within our system. So here's the final design schematic, which I'm going to run quickly and show you guys exactly what the oil does throughout our system. So initially it goes into this, which is a heating and settling tank. The heating and settling tank actually has a funnel underneath it, and it has a heater within. So what we do is we pour the oil into it, we heat it up, and we do it for two reasons. Number one, when you heat the oil, obviously it decreases the viscosity, allowing for a smoother flow throughout the rest of the system. And number two, by heating the oil and allowing it to settle, most of the heavier debris as well as the heavier water within the oil will actually tend to go towards the bottom in the funnel. At this point, we open up this valve right here, which allows the cleaner oil on top to go into the next filter. Once that all goes through, we open up a valve that's directly underneath the funnel, allowing the dirtier oil with the more contaminated debris and water to exit into the debris tank, which is underneath. So once the cleaner oil goes into the system, the first filter that it goes through is this one right here, which is a primary filter. It serves pretty much as a safety for this pump. So in case there's any debris still left within the oil, it will be caught there so it won't damage the pump. The oil is then going to be pumped into the centrifuge, which we actually had to raise up because its outlet is underneath. Underneath, we actually have a three-way valve that when opened one way, the oil can escape into the final storage tank. So the whole point in doing this is, let's say that initially your oil isn't very contaminated, and just by going through the centrifuge once, it's enough to clean it. That's why we have that. When you switch the three-way valve to the other side, it'll go into the next filter, which is a membrane filter. This one actually filters out the thinner debris within the oil that can't actually be taken out by means of gravity. And again, once we do this, we have another three-way valve here and another one down here that when adjusted, it can either go into the final storage tank or to a final filter, which is a water capture filter. This one captures any dissolved water within the oil that can be taken out by means of gravity. Finally, once you're in the final storage tank, we actually implemented a second pump that allows us to recirculate the oil back into the initial storage tank. We did this because let's say that initially your oil is brown grease or it's very dirty and we simply cannot clean it. In one pass through our system, we can actually go ahead and do it as many times as we need to in order to get the final product. So this here is the prototype shown using CAD, and Fabi's going to further talk about this in the analysis.
All right, so here we have the design analysis. We use Bernoulli's equation in order to find the major and minor losses, as well as the total pressure head loss. We also needed to find the friction factor for the PVC piping. Here we have the loss of head for the different flow scenarios. As you can see, the centrifuge flow path, due to the least amount of distance it needed to travel, would have a small amount of head loss. We also have the membrane filter, due to the oil needing traveling a further distance. And then finally, we have the water absorption filter, which, due to, again, the oil needing to travel to the furthest distance to reach the water filter, and then finally the final product tank. The head loss for the water absorption filter at that point was around 33 feet. So in this figure shown, we have the pump performance efficiency curve, and this is actually the pump that was chosen for our system with a volumetric flow rate of around 1.6 gallons per minute. And using the chart, the graph, we were able to find that our pump, our efficiency was suitable for this system. And then these are some of the standards that we focused on while wanting to design and create a reliable system for our senior design. One of the main focuses was safety procedures. So we made sure we followed all the safety procedures when performing the testing as well as the manufacturing. And one of the main focuses was the ASTM D6751. That specification focuses mostly on biodiesel. Vegetable oil contains anywhere from 0.02 to 0.1% of water that's in a dissolved state, as well as the acceptable max of that percentage would be 0.05 of water and sediment to make that purity of oil. So here we have, as shown here in this figure, this in front of you, the prototype fully assembled. The heat and settle tank, as well as the final product tank, is actually insulated with fiberglass in order to prevent any heat from seeping out, as well as protecting the user from the hot tank. We have, as you can see here, due to the level of the prototype, we have the small filter that was mentioned by Rainier. And then we had the centrifuge that had to be raised roughly around 6 inches to accommodate the PVC ball valve. We also have the safety system, as well as the electrical control unit. And then here is a photo showing the funnel that was used to attach to the bottom of the funnel, the heat and settle tank. This would have the debris as well as any remaining water settled at the bottom, as well as the valve open at the end to let out any remaining debris. Here, as spoken previously, was the brass valve, three-way ball valves that we needed to use to accommodate our system. Due to the fact that the valves come differently from what we would like from the factory, we had to make some minor modifications. We had to actually drill a 3/8 inch hole into it to allow the oil flow through our specific way. So we would like to have the oil flow directly across horizontally or straight down. And then here we have a full body view of the prototype of the heat and settle tank with the funnel attached. The funnel was actually riveted as well as sealed with fiberglass and architecture grade silicone. And to perform our testing, we needed to go around to multiple smaller restaurants around the area and collect any waste vegetable oil. It was a dirty task. So pretty much what we had to do was to test the water content of this oil. To test the water content of this oil, we need to we needed to pour it in like 1.5 cups in a beaker, and then have it weighed. We will take down the measurements, and then proceed by putting it in the hot plate. Once we put it in the hot plate, we had it stirred as well as heated up to about 30-35 minutes, and then when we let it cool down, carefully and safely, we'll put it in the scale and measure it again. Now, for the debris testing, we actually got a small coffee filter, and we actually poured the oil, and we collected any debris, as well as putting it on the scale to see how much debris we actually was taking off. So here we have the waste vegetable oil classification chart. This chart would determine which way we would like the oil to flow through. For the centrifuge, anywhere from 0 to 0.3%, we would actually like it to go to the centrifuge and down to the final product tank. The membrane filter would be from 0.3 to 0.8, which is the second filter, and then straight down to the final product tank. And then we have the water capture filter, which is the last filter, and it'll go straight down to the final product tank. Now, anything above 1% in water and debris content, we actually wanted to have it recirculated. So anything that was tested due to the content, we'd actually have it recirculated back into the heat and settle tank, into where we will have it heat up again for roughly around 45 minutes, and then repeat the process. This is a small video of the oil actually going through the centrifuge and flowing through the final product tank. We actually have to change the valves so it goes straight down. So this is we have to manually change the valves ourselves. And then here we have the oil flowing through the 2 remaining filters, as well as the valves, and then exiting down the final product tank. So data analysis, I want to show you guys the before and after. This is actually the oil, the way it looks once we took it from the restaurant, and this is actually the oil that has gone through the system at least once. As you can see, the previous sample I showed you was a brown grease that was stated by Rainier, and then this is something a little more filtered. Yeah, it was filtered. It's yellow grease. So actually, the color indicates the purity, as mentioned, as well as the age and the temperature that the oil was kept in. So there's multiple times where if you have the oil kept in a certain temperature, it actually can affect the purity of the oil. Now I'm going to continue with comparison and testing.
Okay, so here's some of the results that we acquired from one of the samples that we had done. For this in particular is the water testing, for the water content testing. We did 5 separate trials, and the green shows the initial sample weight, and the orange shows the final weight. For this specific sample, we classified it as having a high content water, so we would expect that the water capture would have the greatest results. And here are the results from our debris testing, as previously mentioned by Fabian. As we went on through the trials, we can see that there's a total decrease in amount of weight that was pulled from the filters itself. This is probably attributed to having the debris starting to settle at the bottom of the tank that we were acquiring the samples from, or from us actually pulling out the debris towards the beginning of the testing. Here are the results after we ran it through the first time, or the first time we ran it through the prototype. As you can see here, the blue shows the initial sample weight, the green shows after the centrifuge, the orange shows after the membrane, and the yellow shows after the water capture filter. And from the results that we acquired, we can see that the previous analysis of having a high water content within the sample is validated here because we had the greatest overall change from the water capture filter. Here we have the results after we ran that specific sample one more time through the prototype. For initial heating, we did 100 degrees Fahrenheit, and we ran it through the system again after letting it cool for about 40 minutes. And again, the green shows after the centrifuge, the orange will show after the membrane, and the yellow shows after the water capture. And again, this correlates with the initial classification that we gave the sample. So here's some of the cost analysis for our system. Our total came out to be about $1,600, just shy of it, but with the majority of it being in filtration devices and also within the pumping systems. Here's the initial timeline that we initially came up with. We had a bit of a struggle at the beginning of the summer simply because we had scheduling issues, but we were definitely able to pick up our progress towards the end of the summer, where we were able to acquire all the materials and actually begin manufacturing. We were able to commence and end testing as planned. So some of the benefits of our design is the decrease in overall fossil fuel consumption, because we're using a renewable resource that is not petroleum based. we have a decrease in that, and also there's a decrease in total amount of waste being released into the environment. There have been studies done by various universities where they dumped, they released various amounts of biodiesel and petroleum-based diesel into various controlled environments, and they see that overall there's a greater effect being done by petroleum-based diesel. All right, so some of the places where this thing or the prototype can be used in the concept as well is in foreign countries where it's very tough, where it could be dangerous to send petroleum-based fuels. So since this is a renewable resource being used by multiple civilizations, it can be very easy to acquire. Also, small towns where it's very hard for fuel trucks to get to the separate fuel stations, where it may be cost effective, or it would be more cost effective to just depend on renewable resources, and also organizations that may move around frequently. Some of the environmental impacts is the idea that waste vegetable is a renewable resource simply because it's used by multiple restaurants and by individuals as well to cook their own foods. And also, obviously, there's the decrease in greenhouse gas emissions. There is occasions where they mix petroleum-based fuels with biodiesel in order for a higher combustion rate. But overall, there's a decrease in the total amount of emissions being released. And also, again, like as previously stated, multiple universities have done studies where they saw that there was a higher degradation rate from biodiesel as opposed to petroleum-based diesel in the controlled environments that they dump the substances into. Some of the aspects that we noticed from our project is the increase in local businesses, simply because this kind of system can be used by both an individual and also a wholesale petroleum-based fuel station, or fueling station, sorry. And obviously someone has to man these stations, also someone has to maintain the systems as well, so there's an increase in job availability as well. Also, there's a decrease in foreign dependency, simply because we don't have to send the equipment and machinery to various parts of the world to drill and extract petroleum from, again, various parts of the world. And in conclusion, our system gives us a more purified version of the initial sample, or initial oil that we implement into the system itself. And also, the system can be implemented globally, simply because we can send the same concept or the same prototype over to another part of the world, halfway across the world, and it should give us consistent and reliable results. And also, it's definitely a step forward in green energy, simply because we're using a renewable resource, and if the fuel does get released into the environment by accident or on purpose, there's a higher degradation rate from the biodiesel, which would, I guess, not affect the environment as much. So some of the skills we picked up from this project is the importance of team communication. Being able to work around each other's schedules and limits was very important, and we noticed that in a full year of working together. Also, the idea of working around design constraints such as space, money, and time. Kind of hard to do. Working around that was definitely important, because as engineers we're going to get set timelines and budgets, so we have to work around, and being able to work around obviously was one of the major factors here in this project. And also the idea of the engineering process, because we went from a simple napkin sketch to a fully built prototype and all the steps that went in between. And we definitely noticed that there are certain steps that take longer, even though we expected it to take not so long.
Are there any alternative stock feed that you could consider using to produce this kind of biodiesel?
So, at least from my understanding, we wanted to go and keep it to waste vegetable oil, but there is, from my understanding,
They're also made of animal fats. Anything that has fatty tissues, I guess, can be made into biodiesel.
The reason I ask that question is because in the developing world where you don't have a lot of restaurants that are generating the kind of grease that we're generating here, this would work. So,
Right.
but they might have other stock feed that could be adapted and used. So my question is really, how adaptable is your apparatus here to deal with that kind of variability across our globe?
Well, in a situation like that, the idea would be that it would be much more cost effective to grow your own, I guess, sunflowers or anything, and then remove the oil from that, rather than having to go overseas and purchase the oil from a foreign country. So, yeah.
How clean is clean enough?
want to talk about it?
So ideally, you want the final product to be at least 99% pure in terms of you only have less than 1% of water and debris towards the end. However, due to the fact that the way we tested it using a kitchen scale, we couldn't really estimate how close we got to that. So if we would have had, I guess, better funding, then we could definitely buy better equipment such as a sandy bray test, which actually measures how much water you have within the oil. So as far as how close we got, we're not sure.
Okay, because I would have hoped maybe you would have taken your extremes and then figured out, in the worst case, how many cycles it had to run, and you could say, 10 cycles, I turn to you, and you expect. Okay. How frequently do you have to change filters?
Okay, so what we noticed after running our own samples through here, we noticed that the primary filter here needed to be cleaned out every 2 or 3 runs, simply because occasionally the fat from the oil would back up and it would end up clogging the filter. So initially or occasionally cleaning that is very important. Also, the centrifuge needed to be maintained at least every, I think it was 10 runs that we had done. And it was just simply pulling apart the housing, cleaning off the jets, and then replacing the system. As far as the water capture and the membrane filter, it was all in the specifications.
Yeah, they have a longer reading. I think it's like something like 150 times. I forgot the actual flow rate going through it, but yeah.
Okay, and then my last question is, did anybody think about a cost-benefit analysis? In other words, buying or getting, maybe even getting the oil for free, and the cost of generating this system, how long would it take to have a payback on a system like this?
Well, if we were mass producing this, I mean, I can't tell you like an exact number, but I definitely think that it would be much more cost effective than using gasoline or petroleum, just due to the fact that, I mean, this was $1,600 for us to make because we're only making one. When we make multiple of these, I think it would be obviously drop that price down. So
also, I did a little bit of research prior to this, obviously, and most starter kits for biodiesel production, which includes both filtering and the chemical reaction needed, start at about $2,400. But most of those kits don't give you the chemical agents to actually test the sample and also to create the biodiesel. So I guess I can't give you an accurate number on the benefit or when it is we give you a good profit, but you can see that there's the difference in methods.
So how do you get the oil, and you clean the oil, and that's part A of making your biodiesel. What's part B?
Part B would be the chemical reaction. I don't remember all the chemicals.
right, that would be to produce the actual biodiesel, which is
What
out
do
of the
you
scope
add
of our
to it?
project.
What
Right.
do you add to it?
Well, it's just a chemical reaction it goes through. I'm not a chemistry, but yeah, it's
That's what I want to know. I mean, because it looks like, oh, geez, let's say, so you don't just take the oil that you clean and put it in your car.
No,
You have
well,
to do something else to it.
right. Yeah.
And that step, if it were in this process, then anyone that had a
Right.
car that wanted to run this, you could sell a kit at IKEA and everybody can put one in their backyard, like the Odebrecht guys, right? And that would be a marketable product.
Yeah, we know it's not a complicated process. We've seen multiple YouTube videos of people doing it in their backyards, like producing the actual biodiesel. So knowing how to do that along with having something like this,
Yeah.
you could literally go
I mean,
grocery
because
shopping.
people,
and-
then they could just go to the restaurants. The worst part would be getting the oil.
Yeah,
That's definitely
yeah.
something actually we talked with Dr. Tremonte was adding, or maybe another team could add the next step to it.
Right.
And eventually build a full prototype that would actually produce biodiesel for you.
Yeah, our focusing is mainly
Just the filtration.
filtration.
Well, I got a question, kind of following what he was asking. Let's say you put 1,600 on this,
Yes, sir.
how much money?
Yeah, 1,600, yeah.
1,600. Have you figured out how many gallons of diesel, if you went to the gas station, bought it, how many gallons you gave with that money, and then figure out how many times you'd have to do that, to make an equipment value of
Right, well,
biofuel versus the other fuel?
right, I get where you're coming. We didn't do this. So, right, it would be something to consider to further.
Now, if I can just point out one thing, can you guys go back to any of your bar graphs real quick? Okay. Just as a general rule, kind of be careful with your scaling. I mean, I know the scaling was what it was to show the differentiation between it, but those things that look like 50% reductions are actually 2% reductions. So just be careful. There's other methods. You can standardize the data. You can normalize. I mean, there's other methods that you can do to present it to still show that difference without kind of hiding almost the impact of it.
Thank you. Any questions?
Thank you. That's it. Oh, we're gonna take pictures now?
The picture. Well, we can do one. Should we do one? That's great. Stephanie, you were here? Let me do the
People work through the same thing. Look at this shape.
What?
Look at how big it is. I got like a 1% reduction. I don't. I got called out. Look, it's more than enough. We actually have one woman at work, and that's all she does. Just look at that. She looks at things like that. What are you trying to do?
All right. Let's take a picture. Not after that presentation.